Hello and welcome to Late Night Space. If you enjoy calm, fact-based journeys through the universe, please take a moment to like the video and subscribe. It genuinely helps this channel grow and continue exploring the deeper questions of space. And, if you'd like, leave a quick comment telling me where you're watching or listening from tonight. Now, imagine a star with no galaxy. No neighboring suns, no constellations. Just one star burning alone in the vast darkness between galaxies. This is not science fiction. Astronomers have discovered hypervelocity stars, suns that have been violently ejected from their home galaxies by powerful gravitational interactions. Often, the culprit is a supermassive black hole at the center of a galaxy. When a pair of stars wanders too close, gravity can tear them apart, capturing one and hurling the other outward at such extreme speed that it escapes the galaxy entirely. Once that escape velocity is reached, there is no return. The star crosses the boundary of its galaxy and enters intergalactic space. A realm where matter becomes incredibly sparse, where distances stretch across millions of light years, and where entire galaxies are reduced to faint, distant glows. Inside a galaxy, stars live in crowded systems bound together by gravity and dark matter. They orbit, interact, and share the same gravitational home for billions of years. But beyond the edge of that structure, the universe changes. The cosmic web thins. Voids widen. The night sky, if there were one to observe, would be almost entirely empty. And yet, the star continues to burn. Hydrogen still fuses into helium in its core. Light still radiates outward. The laws of physics remain perfectly indifferent to its isolation. Nuclear fusion does not care whether there are neighbors nearby. But scale does something to perception. A single star drifting alone between galaxies for billions of years challenges how space is usually imagined. It reveals just how empty the universe truly is, and how rare structure can be once gravity loses its hold. Tonight, the journey follows one of these wanderers, a star cast out by gravity, a light traveling through the deepest darkness the cosmos can offer, the loneliest star in the universe. Out there, alone is not a feeling, it is a measurement. In space, isolation is counted in distance and gravity. It is the difference between being held in a vast gravitational family and being so far removed that nothing nearby tugs on you in any meaningful way. No close companions, no busy neighborhood of stars, no shared orbit around a common center. Just a single object, moving through a region where the universe has very little to offer besides emptiness. Most stars never experience anything like that. Most stars live their entire lives inside galaxies, which are enormous gravitational systems built to keep things together. A galaxy like the Milky Way contains hundreds of billions of stars. It also contains gas, dust, and something far more mysterious and far more massive: dark matter. Dark matter does not glow, but it exerts gravity, and it appears to form a broad halo that extends well beyond the visible spiral arms. That halo matters because it deepens the galaxy's gravitational well. It helps keep stars bound, even far from the bright center. This is where the scientific meaning of loneliness begins. A star is at home when it is gravitationally bound. That means its motion is part of a long, stable relationship with the galaxy's total mass. It may drift slightly over time. It may pass through spiral arms. It may wander above and below the galactic disk. But it remains part of the system because the galaxy's gravity still owns its orbit. The basic idea is old. Sir Isaac Newton described gravity as a universal attraction between masses, a rule that works just as well for a falling stone as it does for a star circling a galactic center. In a galaxy, gravity shapes large-scale motion into something surprisingly orderly. Stars orbit the center at speeds that can reach a few hundred kilometers per second. That sounds fast, and it is, but it is not fast enough to break free. Not usually. A key reason is that the visible matter in a galaxy is not the whole story. In the 1970s, astronomer Vera Rubin measured how fast stars orbit in spiral galaxies and found something strange and consistent. Stars far from the center were moving so quickly that the visible matter alone could not explain the gravitational pull keeping them in orbit. Instead of slowing down with distance the way simple expectations suggested, the orbital speeds stayed high. This was one of the strongest pieces of observational evidence that galaxies sit inside massive dark matter halos. Rubin's work did not merely add a footnote, it changed the way galactic structure is understood, because it implied that most of a galaxy's mass is invisible, and that invisible mass is a major reason stars stay bound. So a typical star is not simply floating, it is participating in a shared motion, circling a common center of mass for billions of years. Even the presence of a supermassive black hole at the galactic center fits into this picture, though not in the way films like to suggest. In the Milky Way, Sagittarius, a star, is a supermassive black hole, and it strongly dominates gravity very close to the center. But the orbits of stars in the broader galactic disk are governed mostly by the combined mass of the entire galaxy, especially the dark matter halo. The galaxy is a collective gravitational structure, not a single monster pulling everything by itself. Now step back even further to the star's beginnings. Stars form in cold, dense molecular clouds where hydrogen and helium dominate and heavier elements exist as traces, sprinkled in from earlier generations of stellar death. A small region of a cloud can become slightly denser than its surroundings. Gravity then does what gravity always does. It pulls inward. As gas falls toward the center of collapse, it heats up. Pressure builds. The core becomes hotter and denser until nuclear fusion ignites. In a sun-like star, the proton-proton chain reaction becomes the main pathway, converting hydrogen into helium and releasing energy. That energy pushes outward as radiation pressure and thermal pressure, balancing gravity's inward pull. This balance is called hydrostatic equilibrium, and it is the reason a star can shine steadily instead of collapsing under its own weight. In a galaxy, this kind of star is born into company, not shoulder-to-shoulder company, because even crowded space is still mostly empty, but close enough that the night sky would be busy. Nearby stars could be only a few light years away. Star clusters may form dozens, hundreds, or thousands of siblings together, before spreading out into the wider galaxy. Over time, that star becomes part of the galaxy's rotation, orbiting along with countless others, all bound to the same invisible halo. This is the baseline. This is what normal looks like. So when a star becomes truly alone, something exceptional must happen. It is not enough to drift outward gradually. To become isolated in the harshest sense, a star must be removed from the galaxy's gravitational ownership altogether. Its speed must rise beyond the galaxy's escape velocity, which is the threshold at which motion outward wins over gravitational pull. For a galaxy, that threshold is enormous because the galaxy's total mass is enormous. But nature has a few extreme tricks, and gravity is one of them. There are stars known as hypervelocity stars, moving so fast that their home galaxies cannot hold them. They are not merely speedy, They are unbound. Their paths carry them outward into the halo, and then past the halo, and then beyond everything that once counted as home. A star like that does not simply leave the neighborhood. It leaves the city, leaves the continent, leaves the planet, and keeps going. And once a star is genuinely unbound, the idea of loneliness becomes sharply defined. It is no longer surrounded by a thick field of neighboring stars. It is no longer orbiting inside a dark matter halo. It is moving into intergalactic space, where matter becomes astonishingly sparse, and distances between bright things can stretch across millions of light years. That is the kind of loneliness this story is about. Not emotion, not tragedy, just the cold clarity of gravity, distance, and an object that has slipped free. In most places in a galaxy, gravity behaves like a patient librarian. It keeps stars in orderly orbits, quietly filing them away into spiral arms, halos, and long looping paths that repeat for billions of years. But close to the center of a large galaxy, gravity stops being patient. It becomes steep, fast, and occasionally violent in a very mathematical way. Many galaxies, including the Milky Way, have a supermassive black hole at their center. It is not a cosmic vacuum cleaner prowling the streets for snacks. For most stars, it is simply too far away to matter much. But in the central region, where stars move quickly and the gravitational field is intense, close encounters happen. Orbits cross. Systems get perturbed. Over long spans of time, the center becomes a place where the universe runs experiments on itself. One of the cleanest pathways to a truly expelled star begins with something quite ordinary: a binary star system. Two stars orbiting each other, bound by their mutual gravity, sharing a center of mass like two dancers circling the same point on the floor. Binary systems are common, and many survive for enormous lengths of time. They are stable precisely because gravity, in the two-body case, is beautifully predictable. That predictability ends when a third massive object enters the room. If a binary system passes close enough to a supermassive black hole, the gravitational field is no longer uniform across the pair. The nearer star feels a stronger pull than the farther one. That difference is a tidal force, and tidal forces are not a gentle tug. They are a stretching influence, one that can pull a system apart if the gradient in gravity becomes large enough. This is the heart of the Hills mechanism, proposed by astronomer Jack Hills in 1988. The scenario is almost cruel in its efficiency. A binary star system approaches the supermassive black hole. The black hole's tidal forces disrupt the pair. One star is captured into a tight orbit around the black hole, becoming a new long-term resident of the galactic center. The other star is flung outward at extraordinary speed, launched away from the center like a stone released from a sling. The phrase, gravity's slingshot, sounds like a metaphor, but the engine is conservation of energy and conservation of momentum. In a three-body gravitational interaction, energy can be redistributed between objects even though the total stays the same. The binary system initially has binding energy, the gravitational energy that keeps the two stars together. When the black hole tears the pair apart, that binding energy does not vanish. It is converted. Some of it goes into tightening the orbit of the captured star around the black hole. Some of it goes into the kinetic energy of the escaping star, increasing its speed dramatically. It is worth lingering on what this means physically. Nothing is pushing the star like a rocket. There is no engine, no fuel, no thrust. The star is simply falling through a changing gravitational field and leaving with a different share of the system's energy. The black hole itself does not need to throw anything. Gravity and geometry do the work. When the escaping star's speed is high enough, it becomes what astronomers call a hypervelocity star. That term is used specifically for stars moving so fast that they can escape the gravitational pull of their home galaxy. Inside a galaxy, stars can move quickly and still remain bound, following long elliptical orbits that carry them outward and then back in again. A hypervelocity star is different. It has crossed a threshold. Its trajectory is no longer a closed path. It is an open one, a one-way departure. That threshold is tied to escape velocity, which is the minimum speed required for an object to break free from a gravitational system without falling back. In Newtonian terms, escape velocity depends on the mass of the system and the distance from the system's center. It can be expressed as escape velocity equals the square root of 2 times the gravitational constant times the mass of the system divided by the distance from the center. For a planet, that speed is large but manageable. For a galaxy, where the mass includes not only stars and gas, but also the surrounding dark matter halo, the required speed can be immense. The exact value depends on location and on the galaxy's mass distribution, but the key idea is simple. The galaxy owns a star's orbit unless the star is moving fast enough to climb out of the galaxy's gravitational well. A supermassive black hole interacting with a binary system can provide the necessary conditions. The ejected star can leave the central region at speeds of hundreds of kilometers per second, and in some cases, well beyond that. At those speeds, the star moves outward through the galaxy, crosses the spiral arms, enters the halo, and continues on because its energy budget is no longer compatible with a bound orbit. There is a subtle point hiding inside this, and it matters. The Hill's mechanism is not the only way a star can become fast, but it is one of the most physically direct ways to create a star that is genuinely unbound. It also has a built-in signature. If the star was launched from near the galactic center, its trajectory should, in a broad sense, be consistent with an origin near that region. Not perfectly, because measurements have uncertainties, and the galaxy's gravitational potential is complex, but consistent enough that a population of runaways can point back toward the heart of the Milky Way. All of this would be elegant theory with no bite if there were no evidence. The universe, however, is not shy about leaving clues. The problem is that the clues are faint, and they require large surveys and careful measurement to assemble into a coherent picture. In 2005, astronomer Warren Brown and colleagues reported the discovery of hypervelocity stars associated with the Milky Way. This was not a single dramatic object spotted by luck. It was the product of systematic searching and careful verification. The kind of work that does not look thrilling from the outside, but is thrilling in the way that opening a locked door is thrilling. One of the key resources enabling this era of discovery was the Sloan Digital Sky Survey, often shortened to SDSS. It mapped large portions of the sky and obtained spectra for an enormous number of objects. Spectra are not just pretty rainbows. They are measurement tools. A spectrum allows astronomers to identify absorption lines created by elements in the star's atmosphere, and those lines serve as stable markers. If the star is moving relative to Earth, those markers shift slightly due to the Doppler effect. The Doppler effect is familiar in sound. A siren sounds higher as it approaches and lower as it recedes. Light does not change pitch in the same way, but it changes wavelength. If a star is moving toward the observer, its spectral lines shift toward shorter wavelengths. If it is moving away, the lines shift toward longer wavelengths. By measuring that shift, astronomers can calculate the star's radial velocity, which is its speed along the line of sight. Radial velocity is powerful, but it is only one component of motion. A star might be moving sideways across the sky as well, and that motion does not show up in the radial velocity directly. So the challenge becomes a kind of cosmic accounting problem. How fast is the star really moving through three-dimensional space? And is that total speed greater than the escape velocity of the Milky Way at that location? To answer that, astronomers combine several strands of information. The spectral lines provide radial velocity. The star's brightness and spectral type help estimate distance, because a star's intrinsic luminosity can be inferred from its temperature and classification, and then compared to how bright it appears from Earth. With distance and sky position, motion across the sky can be estimated when proper motion measurements are available, though the accuracy depends on the data quality and time baseline. Even when proper motion is uncertain, extremely high radial velocities are already a strong flag, because they narrow the range of possible total motions. Then comes the crucial step: comparing the star's motion to a model of the Milky Way's gravitational potential. This is where the galaxy's mass distribution matters, including the contribution from the dark matter halo. The halo's mass affects escape velocity, especially in the outer parts of the galaxy. If the galaxy were made only of the matter that shines, escape velocity would be lower, and many stars would escape more easily. But observations of galactic rotation curves, including Vera Rubin's work, imply that dark matter deepens the gravitational well. That makes it harder to escape, which means that a star identified as unbound is truly exceptional. So when Warren Brown and colleagues identified candidate hypervelocity stars, the claim was not simply, "This star is fast." The claim was that the star's speed is incompatible with remaining gravitationally bound to the Milky Way. In other words, given reasonable models of the galaxy's mass and the star's location, the star has enough kinetic energy that its orbit will not loop back. It will keep going. There is also a practical sanity check built into the process. Many fast stars exist in the galaxy, and not all of them are exotic. Some stars belong to the galactic halo population and have high velocities compared to the Sun, simply because the halo has different orbital characteristics. Some stars are members of old populations with eccentric orbits. Some are influenced by past interactions. So the identification of a hypervelocity star requires care, because speed alone is not a badge of exile. What matters is whether the star is unbound. To establish that, astronomers evaluate whether the star's motion exceeds the escape velocity at its position. They consider uncertainties in distance estimates, because distance errors propagate into velocity errors. They consider uncertainties in the Milky Way's mass distribution, because the galaxy's mass is not measured by putting it on a scale. It is inferred through dynamics. The process is not sloppy, but it is honest about what is known and what is uncertain. Even with those uncertainties, some stars stand out as clear outliers. Their measured velocities are so extreme that, across a wide range of plausible assumptions, the conclusion remains the same. The star is leaving. Once such stars were identified, the story became richer. If these stars are produced by the Hills mechanism near the galactic center, then the center becomes not just a place where stars orbit, but a place where stars can be violently expelled. It turns the galactic center into a kind of gravitational accelerator, one that occasionally launches an object into intergalactic space without any need for explosions or jets. Just gravity, geometry, and timing. There is a dark humor to it, if humor can be found in orbital mechanics. A star spends millions or billions of years forming, settling into equilibrium, calmly fusing hydrogen into helium. And then, a single close pass in the wrong neighborhood turns it into a runaway. A cosmic wrong turn taken at a speed of hundreds of kilometers per second, with consequences lasting longer than many galaxies, will remain unchanged. And once the star is on its way out, the departure is not dramatic in the usual sense. It does not leave with a visible trail. It does not blaze like a meteor. It simply moves steadily and relentlessly away from the dense stellar environment that birthed it. It becomes harder to see, not because it stops shining, but because it is traveling into regions where the galaxy's light thins out and the distances to everything else become almost absurd. At that point, the physics of the ejection has done its job. The star has been granted a new kind of identity. Not a star of a galaxy, but a star of intergalactic space. A point of fusion-driven light traveling through emptiness, its path set by a moment of gravitational chaos near a supermassive black hole, confirmed by careful observation and the quiet authority of spectral lines shifting by tiny amounts. The journey outward continues, not as a mystery, but as a consequence. Gravity created the home. Gravity ended the membership. And now, the star moves into the spaces where alone becomes not a metaphor, but a number. A galaxy does not end the way a map suggests it ends, with a crisp line and an immediate drop into nothing. The Milky Way has bright spiral arms and a glowing disk, yes, but that luminous structure is only the densest part of a much larger gravitational system. Beyond the disk, the distribution of stars thins out into what astronomers call the galactic halo. The halo is not empty, but it is sparse. It contains older stars, globular clusters, and streams of stars left behind by smaller galaxies that were torn apart long ago. It is a region where the Milky Way's influence still holds, even when the familiar scenery has faded. And outside the visible halo is something even larger and more important for this story: the dark matter halo. Dark matter does not emit light, but it exerts gravity, and the best current evidence suggests it extends far beyond the bright edge of the galaxy. It deepens the Milky Way's gravitational well and stretches the concept of home far outward. This matters because the true boundary of the galaxy is not defined by where the starlight stops, but by where the galaxy's gravity stops being the dominant influence on a star's motion. That boundary is not a physical wall, it is a threshold in orbital mechanics. If a star is moving slower than the local escape velocity, it remains gravitationally bound, even if it travels far into the halo on a long, looping path. If it exceeds that escape velocity, the orbit becomes open. The star is no longer a returning traveler. It is a departing one. For a star flung outward at hypervelocity, the journey through this outer region is both long and strangely quiet. The star leaves the disk and moves into a realm where the night sky, if there were an observer nearby, would already look different. There are fewer bright neighbors. The star field becomes thinner. The Milky Way's disk would still dominate one side of the sky for a time, but it would slowly shrink as the distance grows. Then scale widens again. The Milky Way is not alone in space. It is part of a small gravitational association known as the Local Group. The Local Group includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. These galaxies are not arranged like beads on a string. They orbit and drift in a complicated gravitational relationship shaped by their masses and by the broader structure of the universe. Yet they do share something important. They are bound together, meaning their mutual gravity is strong enough that the group holds as a coherent system, rather than being pulled apart immediately by cosmic expansion. So the Milky Way's halo is not just the Milky Way's business. It exists inside a wider gravitational environment where other galaxies are also tugging on passing objects. If a hypervelocity star leaves the Milky Way, it does not instantly enter a realm where nothing matters. For a time, it is moving through a space where multiple gravitational influences overlap. But the further it travels, the less those influences resemble a home, and the more they resemble distant background forces. The most extreme loneliness begins when the star is not bound to any galaxy at all. Intergalactic space is often imagined as pure emptiness, and that image is useful, but it needs precision. Between galaxies, there is the intergalactic medium, a very thin gas made mostly of hydrogen and helium, along with traces of heavier elements. It is not dense enough to behave like the gas inside a galaxy. In some regions, it may be only about 1 atom per cubic meter, and even that number can vary widely depending on whether the star is near a filament of the cosmic web or drifting through a deep void. There is also a crucial distinction in modern cosmology between baryonic matter and dark matter. Baryonic matter is the normal matter that makes atoms, stars, planets, and you. It interacts with light. Dark matter does not, at least not in any way that has been directly detected. Yet dark matter shapes the large-scale structure of the universe through gravity. It forms the scaffolding that helps galaxies and galaxy groups assemble in the first place. Where baryonic matter can cool and glow, dark matter cannot. But both influence what a star experiences as it travels outward, because both contribute to the gravitational landscape. A lonely star drifting far from galaxies will encounter the intergalactic medium in the gentlest way imaginable. The density is so low that there is no dramatic collision. There is no visible bow shock carving through a cloud. The star's light passes through a thin sprinkle of particles and keeps going. The star moves through space that is not truly empty, but close enough that, for many practical purposes, it may as well be. Even so, the universe is never completely dark. There is a faint background glow that exists everywhere. The cosmic microwave background radiation. It is the cooled remnant of the early universe, a sea of photons that has been stretching and reddening for billions of years. It does not light up the sky like a sunrise. It is not visible to human eyes. But it is there filling all of space, and it has been mapped in extraordinary detail by missions such as the Planck satellite. Planck did not observe lonely stars directly, but its measurements reveal the large-scale conditions of the cosmos, including the tiny temperature variations in the cosmic microwave background that reflect the universe's early density fluctuations. Those fluctuations are part of the reason the cosmic web exists at all. Now imagine what all this means for something as simple as a night sky. Constellations are a local phenomenon. They rely on a sky crowded enough with nearby stars that patterns stand out. In the Milky Way's disk, this is easy. There are countless stars sprinkled across the sky, and some are close enough and bright enough to draw lines between. But an intergalactic star does not have that field. It does not sit inside a rich, stellar environment. It sits in a sparse realm where neighboring suns may be millions of light years away. That is where the phrase, "a star with no night sky," becomes literal. From the viewpoint of a planet orbiting such a star, there may be almost nothing else to see. The home galaxy would be a distant object, perhaps visible as a faint patch if it is close enough, and if the planet's atmosphere is clear and dark. But it would not fill the sky the way the Milky Way can from within. It would not be a glowing band of light. It would be a faraway island. And beyond that, other galaxies would be even more distant. Millions of light years is a phrase that sounds grand, but still risks becoming a blur. 1 light year is the distance light travels in 1 year. It is already vast compared to anything human travel has ever achieved. 1,000,000 light years is 1,000,000 times that. It is a distance so large that a beam of light leaving a galaxy can travel for a span longer than human civilization has existed, and still be nowhere near arriving at the next major galaxy. For the local group, the separation between the Milky Way and Andromeda is on the order of a few million light-years. That is close by cosmological standards and still utterly beyond everyday intuition. So, in the deep intergalactic environment, a lonely star's sky is not decorated. It is almost blank. There may be faint galaxies like smudges of fog at the edge of vision. There may be a few bright points, but not the dense spray familiar from life inside a galaxy. There may be nothing that resembles a constellation. There is no easy geometry, no familiar anchor points, no sense that the universe is richly populated in every direction. And yet, the star itself shines the same way it always has. Nuclear fusion continues, photons stream outward. The star's light fills its own small sphere of influence, warming whatever worlds might still cling to it, even as the universe beyond that sphere becomes a vast and mostly unlit ocean. At this point, the loneliness is no longer a dramatic idea. It is an environment defined by weak gravity, thin matter, and distances measured in millions of light-years. It is the transition from a galaxy that feels like a structured home to a universe that feels, in the most literal sense, empty. When a star leaves its galaxy behind, distance is only half the story. The other half is time. In a crowded region of a galaxy, nearby can mean a few light-years. That is already a staggering separation on a human scale, but it still allows a night sky rich with stars. Out in intergalactic space, nearby can mean millions of light-years, and at that point the difference between distance and time begins to blur. Because a distance measured in light-years is also a hint about how long light takes to cross it, and how long it would take anything else, moving slower than light, to travel the same gap. A lonely star does not drift at a leisurely pace. Hypervelocity stars can move at speeds of hundreds of kilometers per second, and some are even faster. That sounds dramatic until it is placed against cosmic distances. Hundreds of kilometers per second is fast enough to circle Earth in minutes, but it is still crawling when the next galaxy is millions of light-years away. Even at those speeds, travel becomes a project measured in hundreds of millions of years and beyond. In many realistic scenarios, the star will spend far longer moving through the darkness than any human intuition is built to handle. That raises a strange, quiet question. Does the star itself even live long enough to experience this journey in the purely physical sense of continuing to shine while it travels? The answer depends on the star's mass, because stellar lifetimes are governed primarily by how quickly a star burns through its fuel. This is one of the most important high-level ideas in stellar evolution. Higher mass stars are hotter, brighter, and burn fuel far more rapidly, while lower mass stars burn slowly and can persist for enormous spans of time. Astronomers organize these patterns using the Hertzsprung-Russell diagram, often shortened to the HR diagram. This is a foundational tool in astrophysics that plots stars by luminosity and surface temperature. The diagram reveals that most stars spend the majority of their lives on what is called the main sequence, where hydrogen fusion in the core provides steady energy output. A star's position along that sequence is strongly related to its mass. A Sun-like star remains on the main sequence for roughly 10 billion years. Smaller, cooler red dwarfs can last far longer, potentially for trillions of years, because they fuse hydrogen at a much slower rate. Massive stars, on the other hand, can burn out in only a few million years. They are brilliant, but brief. So if the loneliest star in the universe is a low-mass star, it can remain luminous for a span so long that galaxies themselves can change shape, collide, and merge while it continues shining. If it is a more massive star, it may still be traveling outward while already approaching the end of its life. This is where time becomes unsettling. A hypervelocity star may take hundreds of millions of years to travel a meaningful fraction of the distance between galaxies. That could be only a small slice of the life of a sun-like star and a tiny fraction of the potential life of a red dwarf. It could also be longer than the entire lifespan of a massive blue star. So intergalactic travel is not a single story. It is a story shaped by stellar mass. Eventually, a star reaches the end of core hydrogen fusion. What happens next depends on mass again. Lower mass stars expand into red giants, shedding outer layers and leaving behind a white dwarf. Higher mass stars can continue fusing heavier elements in their cores until they form iron, at which point fusion no longer releases energy, and gravitational collapse leads to a supernova, leaving behind a neutron star or black hole. In the context of a lonely star, the most relevant endpoint is often the white dwarf, because many stars are low mass. A white dwarf is a dense stellar remnant supported not by fusion, but by electron degeneracy pressure, a quantum mechanical effect that resists further collapse. There is an important threshold here known as the Chandrasekhar limit, named for astrophysicist Subrahmanyan Chandrasekhar, who calculated the maximum mass a stable white dwarf can have. Above this limit, electron degeneracy pressure is not sufficient to halt collapse, and the remnant must become something denser, such as a neutron star, or collapse further into a black hole, depending on conditions. The Chandrasekhar limit is often given numerically in textbooks, but the high-level idea matters more for this story. There is a maximum mass at which a white dwarf can remain a white dwarf. Beyond that, gravity wins in a different way. All of this may sound like it belongs to a different topic than loneliness, but it does not. It defines whether the star remains a shining beacon during its long exile, or whether it fades into a dead remnant while still drifting through intergalactic space. And then, there is an even simpler question that often arises when imagining a star in such isolation. Does being alone change the star's life? The answer, in the internal sense, is no. A star's core does not care whether there is a galaxy nearby. Its fusion processes depend on mass, composition, temperature, and pressure inside the star. Those are internal conditions, and they are not meaningfully altered by whether the star is in a spiral arm or in a cosmic void. For a sun-like star, the dominant fusion process on the main sequence is the proton-proton chain reaction. In this process, hydrogen nuclei ultimately combine to form helium, releasing energy in the form of gamma rays and neutrinos. That energy does not escape the star instantly. It is absorbed and re-emitted countless times, slowly working its way outward through the radiative zone, then carried by convection in the outer layers for many stars, before finally escaping as starlight. The star's stability comes from hydrostatic equilibrium, the balance between inward gravitational force and outward pressure. Gravity is always trying to compress the star. The energy produced by fusion provides outward pressure that resists collapse. If the star compresses slightly, the core heats up, fusion rates increase and pressure rises, pushing outward again. If the star expands slightly, the core cools, fusion slows, pressure drops, and gravity pulls it back inward. This self-regulating balance is why main sequence stars are remarkably stable over long spans of time. Radiation pressure plays a role here, especially in more massive stars. It is the pressure exerted by photons as they move outward, transferring momentum to the star's matter. In very massive stars, radiation pressure can be a significant component of the outward force balancing gravity. In lower mass stars like the Sun, thermal pressure and gas pressure dominate, but radiation remains part of the energy transport and balance. None of this depends on external scenery. A star drifting between galaxies still fuses hydrogen. It still maintains equilibrium. It still shines with a spectrum determined by its surface temperature. It still evolves according to the same physical principles described by stellar evolution theory. The proton-proton chain reaction does not slow down because the star has no neighbors. The core temperature does not drop because the nearest galaxy is far away. The star is not powered by the presence of others. It is powered by its own mass and the physics of nuclear fusion. However, there is one subtle way isolation can matter, and it is not internal, it is relational. Inside a galaxy, stars can interact. They can pass near one another. They can exchange mass in binary systems. They can be perturbed by molecular clouds. They can be influenced by dense stellar environments. A star in intergalactic space is largely free from these interactions. It is unlikely to encounter another star closely enough for gravitational capture. It is unlikely to pass through dense clouds of gas. Its evolution becomes almost purely its own. So the lonely star's life is unchanged where it matters most for its light, the core. But it is stripped of the external influences that can complicate stellar evolution, such as mass transfer from a companion, collisions in clusters, or perturbations from dense galactic environments. In that sense, isolation simplifies the star's story. It becomes a clean expression of stellar physics, a fusion engine drifting through the void, carrying its own light and heat across distances so large that the word nearby stops being useful. And the longer it travels, the more the contrast sharpens. Internal continuity, external emptiness. A star can be the loneliest thing imaginable in terms of environment, while remaining, on the inside, the same kind of star the universe has been making for billions of years. When a star is flung out of a galaxy at extreme speed, the first thought is usually about the star itself. A bright point of fusion-powered light, launched into the dark. But the more unsettling thought is what might be clinging to it. Because a star is rarely truly alone in the simplest sense. Many stars host planets. Some host entire systems of worlds, moons, comet belts, and distant icy reservoirs. A star can be a small gravitational home, and the question becomes quietly practical. If the star is thrown away, does the home come with it? The answer depends on how the star was ejected, how violent the gravitational encounter was, and how tightly those planets were bound in the first place. In the calm, orderly parts of a galaxy, a planetary system can remain stable for billions of years. But a hypervelocity star is not produced by calm. It is produced by a close encounter with something extreme, often involving a supermassive black hole and a binary star system being torn apart. That kind of encounter can be brutal for anything orbiting either star. If a star passes close enough to a supermassive black hole for the Hill's mechanism to occur, the gravitational gradient across the region is enormous. The black hole's tidal forces do not merely separate the two stars. They can tug on the extended outskirts of a planetary system as well. Far-out planets, comet clouds, and loosely bound debris are the first to be stripped away, simply because their orbital binding energy is relatively small. Even within a normal planetary system, the outer regions are held less tightly than the inner ones, and in a strong gravitational encounter, the outermost parts are the easiest to peel off. So a lonely star may depart with its inner worlds intact, but leave behind its distant companions. A compact set of planets close to the star might survive, while everything beyond could be scattered, captured, or left drifting on independent orbits. In some cases, the planetary system could be destabilized entirely. Planets might be flung into rogue trajectories of their own, becoming free-floating worlds that wander without any star at all. there is another complication. Many of the most efficient ejection scenarios involve binary stars. Binary dynamics can already make planet formation and long-term stability more difficult, depending on the spacing of the two stars and the architecture of the system. Some planets in binary systems orbit one star closely, in what is called an S-type orbit. Others orbit both stars together in what is called a circumbinary orbit. Both arrangements can be stable, but stability depends on distance ratios and gravitational perturbations. Add a supermassive black hole encounter, and those delicate long-term balances can be shattered. And yet, despite all that, it is entirely plausible that some hypervelocity stars carry planets. Not because the universe is kind, but because gravity is selective. The closer a planet orbits to its star, the more tightly it is bound. A small, rocky planet close in, completing an orbit in days or weeks, can be far harder to strip away than a distant, icy body that takes thousands of years to make one circuit. So the most likely companions of a runaway star are the ones hugging close to their sun. This idea is not just a storytelling flourish. It fits naturally with what has been learned about planets in general. The Kepler mission, run by NASA, revealed that planets are common, not rare treasures sprinkled sparingly across the galaxy, but frequent outcomes of star formation. Kepler detected thousands of exoplanet candidates and confirmed many of them, using the transit method, where a planet passes in front of its star and causes a small, regular dip in brightness. From that simple measurement, combined with careful follow-up work, astronomers learned that small planets are abundant and that many stars host multiple planets. Kepler also showed something that matters here. Compact systems are real. Many stars host tightly packed families of planets, with several worlds orbiting closer to their star than Mercury orbits the Sun. Those close-in systems, if they formed around a star that later became a hypervelocity runaway, are the ones most likely to remain with it. A lonely star drifting between galaxies could, in principle, still have a handful of worlds circling it, still tracing their regular paths as if nothing happened, while the broader universe outside their tiny gravitational bubble stretches into emptiness. If such worlds exist, their sky would be almost impossible to describe in familiar terms. There would be no constellations, no thick band of the Milky Way. Perhaps a faint, distant glow where the home galaxy used to be, and beyond that, a few other galaxy smudges, dim and far. But their day-night rhythm would still be driven by a nearby star. Seasons, if their orbit and tilt allow it, might still come and go. Oceans might still rise and fall under the pull of moons. In the small local sense, life could still measure time normally, even while the wider universe becomes almost blank. The strange truth is that the most dramatic cosmic exile does not necessarily destroy the smallest routines. A planet can keep orbiting. A moon can keep tugging on tides. Even the light from the star would feel familiar, because the star's spectrum and intensity depend mostly on the star's own properties, not the scenery around it. But companionship in space is not only about planets. Stars are often born in clusters. Many retain stellar companions. Some interact with passing stars and clouds. A star in intergalactic space loses nearly all of that. It becomes, in a practical sense, a gravitational island. Its local system may remain, but the broader ecosystem is gone. And that loss of environment is what brings the mind naturally to the next question. If galaxies are the places where structure lives, what does the space between galaxies truly look like on the largest scales? Because intergalactic space is not uniform. It has geography in a cosmic sense. Not mountains and oceans, but filaments, clusters and voids. The universe has a large-scale architecture sometimes called the cosmic web. Galaxies tend to form along filaments of matter, where density is slightly higher. Galaxy clusters collect at nodes where filaments intersect. And between those filaments and clusters lie cosmic voids, regions of space that are dramatically underdense compared to the cosmic average. Voids are some of the emptiest places known, but they are not perfect nothingness. They still contain matter, just far less of it. They may contain small, faint galaxies, thin gas and dark matter, but the density is low enough that the region feels like a vast subtraction. If a lonely star were to drift into a deep void, the isolation becomes even more extreme. It is not merely outside a galaxy, it is outside the bustling intersections of the cosmic web, drifting in the wider gaps between the universe's main structures. Much of what is known about these vast patterns comes from a combination of observation and simulation. Observationally, astronomers map the positions of galaxies across large volumes of space and see the filamentary pattern emerge. Computationally, simulations allow scientists to start with early universe conditions inferred from the cosmic microwave background and evolve them forward under gravity, watching how structure forms. One of the most famous large-scale structure simulations is the Millennium Simulation, run by an international collaboration including the Max Planck Institute for Astrophysics. In this kind of simulation, dark matter is modeled as a vast set of particles whose gravitational interactions are computed over cosmic time. As the simulated universe evolves, dark matter collapses into halos. Halos merge and grow. Filaments form. Voids open up. Then, using additional modeling, galaxies are placed into these halos based on the physics of gas cooling, star formation, and feedback processes. The Millennium Simulation is not a perfect replica of reality, and no simulation is, but it captures a crucial high-level truth. Gravity amplifies small initial differences. Slightly denser regions attract more matter, become denser still, and eventually form clusters and filaments. Slightly emptier regions lose matter to their surroundings and become emptier over time. Voids are not merely empty by chance, they are empty because matter flows out of them as the universe evolves. This matters for the loneliest star because it explains why there are places where loneliness is not just a poetic label, but an inevitable physical condition. If a star is unbound and moving through intergalactic space, it is moving through a universe that has already separated itself into dense and sparse regions. If it wanders into a void, the chance of encountering anything meaningful becomes extraordinarily small. Now, the phrase deepest darkness can be misleading if it suggests that darkness is caused by something actively swallowing light. In reality, intergalactic darkness is mostly a consequence of geometry and distance. Light spreads out. Bright objects become dim with distance. The number of nearby luminous objects drops. The background glow is faint. It is not that darkness is a substance. It is that the supply of light sources becomes sparse. Still, there is a deeper layer to the story of emptiness, and it is not about where matter is. It is about how space itself changes over time. The universe is expanding, not in the sense that galaxies are flying through a fixed space like shrapnel, but in the sense that space between unbound objects is stretching. This expansion was first described observationally by Edwin Hubble, who found that galaxies are, on average, moving away from us, and that more distant galaxies recede faster. This relationship is known as Hubble's law. In modern cosmology, the expansion is not only continuing, it appears to be accelerating. That acceleration was discovered in the late 1990s through observations of Type 1 as supernovae, which serve as standardizable candles for measuring cosmic distances. Research teams including Saul Perlmutter, Brian Schmidt, and Adam Rees found that distant supernovae were dimmer than expected in a decelerating universe, implying that the expansion has been speeding up over time. The simplest explanation for this acceleration is dark energy, a term used to describe whatever is driving the accelerated expansion. Dark energy is not understood in a complete way. The most straightforward model treats it as a cosmological constant, an energy density inherent to space itself. In that picture, as space expands, the amount of dark energy increases in total because there is more space, even though the density remains constant. That leads naturally to acceleration. This is where loneliness begins to take on a long-term, almost permanent character. In an accelerating universe, unbound objects tend to drift farther apart over time. Galaxies and clusters remain gravitationally bound to each other. Stars within galaxies remain bound. But between clusters and between unbound objects, distances grow. Over immense spans of time, the observable universe becomes more fragmented, with bound regions becoming isolated islands separated by expanding space. This framework is part of what is called the lambda cold dark matter model, often shortened to the standard cosmological model. In this model, the universe contains ordinary baryonic matter, cold dark matter that moves slowly compared to the speed of light and clumps under gravity, and dark energy represented by the Greek letter lambda, indicating a cosmological constant-like component driving acceleration. The model explains a wide range of observations, including the large-scale distribution of galaxies, the cosmic microwave background patterns, and the growth of structure over cosmic time. Now bring this back to a runaway star. A hypervelocity star is not bound to its galaxy. Once it is truly unbound, its path is determined by its initial velocity, the gravitational fields it passes through, and the overall expansion of the universe on very large scales. Locally, gravitational forces dominate. The star's motion is mostly a straight trajectory through weak gravitational fields, with gentle deflections if it passes near massive objects. But over intergalactic distances and over billions of years, cosmic expansion becomes relevant as part of the broader framework in which the journey occurs. It is important not to overstate this. Cosmic expansion does not pull apart bound systems. It does not stretch the solar system. It does not inflate a star. Gravity and electromagnetic forces hold those systems together. But for objects that are not gravitationally bound to each other, the expansion contributes to increasing separation over time. A star drifting between galaxies is, by definition, not tightly bound to the galaxies it passes. So its separation from those galaxies can grow, especially once it is far from major gravitational structures. The subtlety is that the star still has a velocity through space that can be much larger than the expansion-related recession over smaller intergalactic distances. If the star is launched at hundreds of kilometers per second, that motion dominates its immediate travel story. Yet the universe is patient. Over billions of years as the star moves through the cosmic web, the overall expansion sets the background conditions. Regions not bound together drift apart. The cosmic web continues to evolve. Voids can become emptier. Clusters can become more isolated from one another as acceleration increases. So what does drifting through cosmic expansion actually mean for the loneliest star? It means that there may be fewer opportunities for the star to ever be recaptured. It means that if the star misses a filament or passes between major structures, the universe's large-scale trend is not to bring things back together, but to separate them. In a decelerating universe, gravity could, in principle, slow expansion and allow more re-merging of large-scale structures. In an accelerating universe, the opposite tendency dominates beyond bound regions. Over the deepest times, the lonely star is not just far from home. The definition of home itself becomes less available. It also means that the star's view of the universe, if it had an observer, would slowly change in a very specific way. Distant galaxies would become more red-shifted over time. Light would take longer to arrive. Some regions might eventually pass beyond the cosmic horizon, meaning their light could never reach the star no matter how long it waited, because the space between expands too quickly. This is not immediate for local structures, but it is a real consequence of accelerated expansion on the longest scales. For a star with planets, this has a strange implication. The local system could remain stable while the observable universe outside becomes less populated over time. The sky could become emptier, not because objects vanish, but because they become unreachable and invisible. A planet could still see its sun rise and set while the wider cosmos slowly fades into fewer and fewer accessible lights. And there is one more grounded detail that makes the story feel even quieter. Intergalactic space, even in voids, is not completely inert. There is gas in the intergalactic medium, thin enough to be nearly irrelevant, but present. There are weak magnetic fields on large scales. There is background radiation. A star drifting for billions of years is moving through an environment that is almost nothing, but never quite nothing. The star's light interacts with that environment in subtle ways, ionizing sparse gas, pushing on dust if any exists nearby, and adding, in its tiny local region, a flicker of activity to a place dominated by absence. So the lonely star's loneliness is layered. On the smallest scale, the star might still host planets, perhaps even an inner set of worlds that survived the ejection intact. On the intermediate scale, the star is stripped of neighbors, of clusters, of encounters. On the larger scale, the star is moving through a universe whose structure is shaped by cold, dark matter, and whose future is influenced by dark energy. Voids become deeper. Bound structures become islands. Expansion sets the long-term trend. Through all of it, the star continues to shine, indifferent and steady, a fusion engine whose local gravity still holds whatever small system remains. And that is the quietly unsettling contrast at the heart of the loneliest star in the universe. A small, stable world could orbit a star that has been exiled from its galaxy, while the universe, on its grandest scales, keeps stretching the distances that make exile feel permanent. A star can be flung into intergalactic space and still look, for a long time, like an ordinary sun. It shines. It warms whatever might still orbit it. It burns through hydrogen in its core with the same steady patience as any other main sequence star. The universe does not mark its exile with a special color or a dramatic halo. It simply lets the star continue. But the far future does not care where a star lives. The far future cares about mass, fuel, and time. If the lonely star is low in mass, it can remain on the main sequence for an almost unreasonable span of time. In the calm arithmetic of stellar evolution, small stars are misers. They sip fuel rather than gulp it. They shine dimmer, but they keep going, and going, and going, long after brighter stars have already burned out. A sun-like star is more impatient, lasting on the main sequence for roughly 10 billion years before it begins to change. Massive stars, bright and short-lived, may not stay luminous long enough to travel very far from home before they reach their end states. Eventually, though, every ordinary star runs into the same constraint. Core hydrogen becomes scarce. Fusion in the core slows. the delicate balance of hydrostatic equilibrium shifts. Gravity presses inward more effectively. The core contracts and heats, and the outer layers respond. For many stars, this means expansion into a red giant phase, where the star's outer envelope swells and cools, while the core becomes denser and hotter. For a lonely star, this transformation would happen in profound darkness. There would be no nearby stellar crowd to witness it, no spiral arm backdrop, no rich galactic sky. Just the star itself, changing shape and brightness on the schedule written by its mass. If the star is similar to the Sun or smaller, the likely outcome is a white dwarf. A white dwarf is the exposed core left behind after the star sheds its outer layers. The shedding can create a planetary nebula, a glowing shell of gas, but that glow fades with time as the gas disperses into the surrounding medium. In intergalactic space, that dispersal might feel almost symbolic, but the physics is straightforward. The material expands into an environment that is already extremely thin, and over time it becomes part of the intergalactic medium. The white dwarf that remains is a dense, Earth-sized object with a mass comparable to the Sun's. It no longer produces energy through fusion. Instead, it shines from residual heat, slowly cooling over immense spans of time. It is supported against further collapse by electron degeneracy pressure, a quantum mechanical effect that comes from the rules governing how electrons can be packed together. In plain terms, the electrons resist being squeezed into the same states, providing a pressure that does not depend on temperature the way ordinary gas pressure does. White dwarfs have a maximum stable mass, known as the Chandrasekhar limit, named for astrophysicist Subrahmanyan Chandrasekhar. If a white dwarf's mass exceeds that limit, electron degeneracy pressure cannot hold gravity back, and the object must collapse further. In most isolated cases, a lone star does not gain mass, so this limit is more of a boundary condition than an imminent threat. But it remains one of the key signposts in understanding how matter behaves under crushing gravity. If the original star is more massive, the ending can be more dramatic. After core hydrogen is exhausted, a massive star can continue fusing heavier elements in shells, and eventually in the core, stepping through carbon, neon, oxygen, and silicon burning. This chain ends at iron. Iron fusion does not release energy, it consumes it. At that point, the star loses its ability to support itself through fusion energy, and the core collapses. That collapse can lead to a supernova explosion, leaving behind either a neutron star or a black hole, depending on the mass of the core and the details of the collapse. A neutron star is an object where matter has been compressed so intensely that electrons and protons have largely combined into neutrons, and the star is supported by neutron degeneracy pressure and other nuclear forces. It is extraordinarily dense, with a mass comparable to the Sun's packed into a sphere roughly the size of a city. A black hole in this context is the outcome when collapse continues beyond the point where any known pressure can halt it. The object becomes a region where gravity is so strong that within a boundary called the event horizon, not even light can escape. There is nothing about intergalactic space that changes these outcomes. A massive star in exile can still die violently. A smaller star can still fade into a white dwarf. The endings are written inside the star, not in the landscape around it. Then, beyond the life cycle of any single star, there is the far future of the universe itself. And this is where the loneliness becomes almost absolute. In the standard cosmological picture, the universe expands, and that expansion is accelerating due to dark energy, often treated as a cosmological constant-like component in the lambda-cold dark matter model. Over time, gravitationally bound systems remain intact. Galaxies hold together, galaxy clusters hold together. Stars remain bound to their galaxies if they are not already unbound. But beyond those bound islands, space continues to stretch. As the universe ages, the overall trend is toward greater separation between unbound structures. The night sky, as seen from any location, would gradually lose accessible galaxies. More distant galaxies would become increasingly redshifted, their light stretched to longer wavelengths. Over immense spans of time, many would pass beyond the cosmic horizon, meaning their light could never reach an observer, no matter how long one waited, because the space between expands too quickly. This leads naturally into one of the most discussed long-term scenarios: heat death. Heat death is not an explosion. It is not a collapse. It is a slow drift toward maximum entropy, where energy gradients become smaller and smaller, and the universe approaches a state where little useful work can be extracted, because everything is, in a sense, spread out and settled. In such a future, stars stop forming because the raw materials become too diffuse or locked away in remnants. Existing stars burn out, white dwarfs cool, neutron stars cool, black holes remain, and over unimaginably long times they can evaporate through Hawking radiation, a quantum process proposed by physicist Stephen Hawking, where black holes are predicted to lose mass very slowly by emitting radiation. This evaporation is so slow for stellar mass black holes that it is almost comical to call it slow. It is slow on a scale that makes the age of the current universe feel brief. For a lonely star, or what remains of it, this cosmic future adds another layer. Even if the star once drifted between galaxies with a few faint smudges visible in the distance, the long-term trend is that those smudges become fewer, dimmer, and eventually unreachable. The star's isolation is not only spatial, it becomes historical. It becomes a consequence of cosmic evolution. If the lonely star ends as a white dwarf, it would cool in a universe where the background temperature itself continues to decline as expansion stretches radiation. If it ends as a neutron star, it would become a dark, cold object in the same long silence. If it ends as a black hole, it would persist far longer than most familiar objects, quietly shaping the near space around it through gravity, long after starlight has become rare. In the heat death picture, the universe does not go out with a bang. It fades with extraordinary patience. A star's exile becomes part of a broader trend, a cosmos that slowly makes everything more separate, more diffuse, more quiet. And yet, here is the twist that keeps the story grounded. Even in this deeply quiet future, the universe is not truly empty. It is filled with the consequences of its own past. Background radiation, thin particles, and the faint traces of earlier structure remain. The cosmos becomes less hospitable to complexity, but it does not become nothing. It becomes subtle. That brings attention back to the present universe, because the most practical question is not only what happens to one lonely star, but how many such stars might exist right now. If a star can be ejected, it is reasonable to suspect that the universe has produced more than one. In fact, there are environments where intergalactic stars may be common, not because stars enjoy wandering, but because gravity in crowded systems can be ruthless. One such environment is a galaxy cluster. A cluster is a collection of galaxies bound together by gravity, embedded in a massive dark matter halo, filled with hot gas that emits X-rays, and shaped by repeated interactions over billions of years. In these clusters, galaxies do not live quiet, isolated lives. They pass close to one another. They merge. They tug at each other through tidal forces. They can strip stars from one another during close encounters. When stars are stripped from their home galaxies within a cluster, they can become intra-cluster stars, drifting in the space between galaxies inside the cluster. This is not quite the same as truly intergalactic space between clusters, but it is still a form of exile. The star is no longer bound to a single galaxy. It becomes part of the cluster's broader gravitational environment. How can such stars be detected? Often, not as individual points, but as a diffuse glow called intra-cluster light. Intra-cluster light is a faint, extended brightness spread through the cluster, produced by stars that are not contained within any one galaxy. Detecting it is difficult because it is dim and spread out, and because telescopes must carefully subtract foreground light, background light, and instrumental effects. But with deep imaging and careful analysis, it can be measured. The Virgo cluster, the nearest large galaxy cluster to the Milky Way, has been a key target for such studies. Virgo is a rich environment of galaxies, including giant ellipticals and spirals, and it is close enough that it can be studied in detail compared to more distant clusters. Observations with the Hubble Space Telescope and other instruments have contributed to the broader understanding of cluster structure, galaxy interactions, and faint stellar components. A notable approach in Virgo has involved looking for tracers that reveal intra-cluster stellar populations. One tracer is planetary nebulae, because they can be bright in specific emission lines and can be detected even when the surrounding stellar light is extremely faint. Another tracer is globular clusters, which can be stripped and wander as well. Deep optical imaging can reveal faint streams and diffuse light that hint at a history of gravitational stripping and disruption. So when asking whether there could be millions of lonely stars, the answer depends on what kind of loneliness is being discussed. Truly intergalactic stars roaming the vast voids between galaxy groups are likely far harder to count because they are isolated and dim with distance. But intra-cluster stars drifting between galaxies inside clusters may be numerous enough to contribute a measurable fraction of a cluster's total light. Estimates vary across clusters and methods, but the broad conclusion is that intra-cluster light can account for a significant portion of a cluster's starlight. That implies an enormous population of stars that have been removed from their original galaxies. In other words, the universe may contain not just a few wanderers, but vast armies of them, quietly lighting the spaces between galaxies in the busiest cosmic cities. There is something almost ironic in that. The loneliest star in the universe is defined by solitude, yet the mechanisms that create lonely stars may operate most efficiently in crowded places. Galaxy clusters, with their repeated gravitational encounters, are star-making factories in one sense, and star-liberating factories in another. They take the ordered membership of galaxies and shuffle it, strip it, and redistribute it into a faint communal glow. From far away, that glow is almost ghostly. It does not form a crisp shape. It does not announce itself loudly. It is a quiet smear of starlight, evidence that gravity has been rearranging the universe for billions of years, pulling some stars into tighter homes while flinging others into wide, lonely trajectories. If that is true inside clusters, it suggests something larger as well. Over cosmic time, gravitational interactions do not only build structure, they also create outliers. Every merger, every close pass, every disruption has the potential to produce stars that no longer belong to a single galaxy. Some will remain inside clusters. Some may be launched outward into the broader intergalactic medium. And while the most isolated wanderers are the hardest to detect, their existence is a natural consequence of the same gravitational physics that shapes galaxies in the first place. So the far future of a lonely star is, in one sense, the far future of all stars. Fuel runs out, remnants remain. The universe trends toward higher entropy. But the present population of lonely stars may be far larger than intuition suggests, hidden in faint intracluster light, revealed by deep imaging and implied by the restless gravitational history of galaxy clusters, like Virgo. A star can be lonely because it is far away. It can also be lonely because it has been unclaimed, not destroyed, not extinguished, simply no longer assigned to a single galaxy's embrace. And in a universe built from gravity and time, that may be less of an exception than it first appears. Finding a lonely star between galaxies sounds at first like trying to hear a whisper during a hurricane. Not because the star is quiet, but because the universe is large, and distance is a brutal editor. Light spreads out as it travels. The farther away a star is, the dimmer it looks, even if it is burning as fiercely as any sun ever did. So the first challenge is simple and unromantic. A star can only be studied if it can be detected, and detection depends on light, distance, and time. In the Milky Way, the situation is forgiving. There are stars close enough that their positions can be measured with exquisite precision. That precision is the domain of astrometry, the science of mapping where objects are in the sky and how their positions change. This is where the European Space Agency's Gaia mission becomes one of the most important instruments in modern astronomy. Gaia does not take glamorous portraits. It takes measurements. It repeatedly observes enormous numbers of stars, tracking their positions and tiny changes in those positions over time. From these changes, astronomers can infer proper motion, which is how a star moves across the sky, and they can measure parallax, the subtle apparent shift in a star's position caused by Earth's orbit around the Sun. Parallax is one of the most direct methods for determining stellar distance. If the baseline is Earth's orbit, then the shift in apparent position over that orbit can be translated into distance. The idea is straightforward. The practical difficulty is that the shifts are tiny. For nearby stars, parallax is measurable. For very distant stars, the angle becomes so small that it approaches the limits of instrumentation and noise. That is a crucial limitation for this story. A truly intergalactic star, far outside the Milky Way and far from any nearby galaxy, may be too distant for parallax to be measured reliably. At that point, distance estimates rely more heavily on indirect methods. Astronomers may use a star's spectrum to estimate its temperature and type, infer its intrinsic luminosity, and compare that to its observed brightness to estimate distance. This method is powerful, but it comes with uncertainties. Small uncertainties in stellar classification can become large uncertainties in distance, and large uncertainties in distance become large uncertainties in total velocity. Velocity is the other half of the problem. A hypervelocity star is defined by motion. It is not enough to see it. The star must be identified as fast, and more importantly, as unbound. Radial velocity, the motion toward or away from Earth, can be measured through the Doppler effect using spectral lines. But to know whether a star is truly escaping the Milky Way, astronomers need the full, three-dimensional motion as best they can manage. Proper motion provides sideways motion across the sky. Distance converts that proper motion into true transverse velocity. Radial velocity provides the line-of-sight component. Combine them, and a star's total speed through space can be estimated. Then comes the final comparison, and it is always the same question asked in a different accent. Given the star's position and motion, and given the Milky Way's gravitational potential, is the star bound or unbound? The gravitational potential depends on the mass distribution of the galaxy, including its dark matter halo. That halo is not directly visible, but it is inferred from the motions of stars, gas, and satellite galaxies. So the answer is not a single crisp number. It is a probability shaped by measurement uncertainties and by the remaining uncertainties in the galaxy's mass model. When a star is moving at an extreme speed, the conclusion can be robust, even with uncertainties. When a star is near the borderline, astronomers have to be careful. Science does not reward confidence. It rewards accuracy. The difficulty increases sharply beyond the Milky Way. Inside the local group, there are opportunities. The local group includes the Milky Way and Andromeda, and because those galaxies are relatively nearby on cosmic scales, some individual stars can still be studied, though not with the same ease as stars within the Milky Way. But beyond the local group, individual stars become far harder to resolve and characterize. Distant galaxies blur into collections of unresolved light. Individual stars vanish into the combined glow. At that scale, a lonely intergalactic star becomes a needle not just in a haystack, but in a fog bank. That does not mean such stars do not exist. It means that detection becomes biased toward the nearest, brightest, or most unusual examples. It also means that much of what is inferred about the population of intergalactic stars comes not from spotting them one by one, but from studying faint diffuse light in galaxy clusters, or from tracing the aftermath of galaxy interactions that should logically produce unbound stars. In other words, the universe does not hand over its loneliest objects willingly. They have to be extracted from the data with patience. And there is another subtle barrier: time. To measure proper motion cleanly, a long baseline helps. The longer the observation span, the more confidently a tiny shift can be separated from noise. That is why missions like Gaia are so valuable and why future missions and long-term surveys matter. The cosmos is always moving, but the motions are often small on human timescales. Precision astronomy is partly the art of waiting. So when asking how these stars can be seen, the answer is that they are seen through a combination of careful light measurement, astrometric precision, spectral analysis, and realistic modeling of galactic gravity. And beyond the nearest cosmic neighborhood, many of them are not seen individually at all. They are sensed statistically through the faint traces they leave in the distribution of light. Once that reality sinks in, it changes how the mind approaches the story. The loneliest star becomes not just an object drifting somewhere, but an example of how measurement meets scale. And scale has a peculiar effect. It rearranges meaning. Carl Sagan captured that rearrangement in one of the most enduring images of modern astronomy: the pale blue dot. The phrase refers to Earth, photographed as a tiny point of light from far away, framed against an enormous darkness. The science in that image is simple. Earth is small, space is large, but the emotional and philosophical impact comes from what the image does to perspective. It makes the familiar feel fragile, and it makes the vast feel indifferent. A lonely star between galaxies does something similar, but in a different direction. The pale blue dot reminds you that even an entire world can be reduced to a speck in the cosmic view. The lonely star reminds you that even a sun can be removed from its community and set adrift in a region where the universe barely offers any reference points at all. It is tempting, at that moment, to turn the story into a metaphor about human loneliness, about isolation, about meaning. But that temptation can quietly distort what the universe is actually showing. Anthropocentrism is the habit of placing human experience at the center of interpretation. It is natural because minds evolve to navigate social groups on a small planet, not to interpret intergalactic space. But cosmology is not obligated to fit the shape of human intuition. The cosmos is not built to be emotionally legible. It is built, as far as can be told, to obey physical law. That does not mean reflection is forbidden. It means reflection works best when it stays anchored to reality. The most honest form of wonder is not to project feelings onto the star, but to let the star reveal something about scale. A galaxy can hold hundreds of billions of stars, and yet gravitational interactions can still eject one into the void. The cosmic web can stitch matter into filaments and clusters, and yet it can also contain voids so large that the word empty becomes almost meaningful. The universe can be richly structured in some places and profoundly sparse in others, and both realities exist at the same time. In that sense, the story is not about the star's loneliness. It is about the universe's range. A mind wants categories, home and away, crowded and empty, near and far. But cosmological scale blurs these categories into gradients. The edge of a galaxy is not a wall. The space between galaxies is not pure nothingness. Even darkness is not absolute, because the cosmic microwave background radiation fills all of space, a faint afterglow of the early universe. So what does scale mean if meaning is not built into the universe? Scale means that the same physical rules operate across domains so different that language struggles to compare them. The same gravity that guides a falling stone also shapes a galaxy cluster. The same thermodynamics that describes heat in a cup of tea also describes the long-term trend toward higher entropy in the cosmos. The same conservation laws that keep a pendulum honest also keep a star's ejection from a supermassive black hole mathematically accountable. And that is where the story settles into a colder, clearer truth. The universe does not notice. That statement is not despair, it is description. Natural laws do not have preferences. Gravity does not punish. Expansion does not intend. Fusion does not choose. The universe does not reward belonging or penalize exile. A star is bound because the numbers say it is bound. A star escapes because the numbers say it escapes. Entropy is one of the clearest examples of this indifference. In thermodynamics, entropy describes the number of ways a system can be arranged, and the overall tendency is that systems move towards states with higher entropy, because there are more ways to be disordered than ordered. This is not a moral statement, it is a statistical one. It is the reason hot things cool, why mixed things stay mixed, why energy gradients flatten over time. On cosmic scales, this trend plays out in slow, vast ways. Stars burn their fuel. They convert mass into energy. They radiate that energy into space. Over time, energy becomes more spread out, less concentrated, less available for structured work. This is part of why the heat-death idea exists as a long-term scenario. It is not a prophecy of sadness. It is the logical extension of thermodynamics applied to a universe that keeps expanding. Gravity complicates this story because gravity can create structure even as entropy increases. Matter can clump, stars can form, galaxies can assemble. It can look like order is increasing. But in the deeper accounting, this is not a violation of thermodynamics. Gravitational systems can increase entropy through the release of energy as they collapse. Heat is produced, radiation is emitted. The overall entropy of the universe still increases. Gravity builds islands of structure while the broader thermodynamic trend continues. That continuity of physical law has a long lineage. Sir Isaac Newton provided a framework for gravity that remains extraordinarily useful for most everyday and many astronomical calculations. Newton's law of universal gravitation treats gravity as a force between masses. It works well for predicting planetary orbits and many aspects of stellar and galactic motion. Albert Einstein reframed gravity through general relativity, describing it not as a force in the usual sense, but as the curvature of space-time caused by mass and energy. In Einstein's picture, objects follow paths called geodesics through curved spacetime. This framework becomes essential near extreme masses such as black holes, and it underpins modern cosmology, including the expanding universe. Both pictures, used appropriately, describe the same universe. They are not competing moods. They are tools tuned to different regimes, and both lead to the same blunt conclusion for the lonely star. Whether described by Newtonian mechanics or by general relativity, the star's exile is a consequence of gravity behaving consistently. The star was bound because gravity held it. The star escaped because gravity, through a three-body interaction, transferred enough energy for it to exceed escape velocity. The laws did not bend to accommodate narrative. The narrative bent to accommodate law. This is the quietest kind of unsettling. Not that the universe is hostile, but that it is uninterested. A star can drift between galaxies for billions of years, shining steadily, while the large-scale universe expands around it. It can cross regions of the cosmic web where matter is slightly denser, and then regions of deep void where almost nothing is. It can carry planets or lose them. It can end as a white dwarf, a neutron star, or a black hole depending on its mass. And throughout all of it, the governing principles remain the same. Gravity shaping motion, fusion producing light, thermodynamics guiding energy toward diffusion, and space-time providing the stage without commentary. In that sense, the loneliest star becomes a kind of demonstration. It shows that belonging is not a cosmic category. It is a temporary gravitational arrangement. It shows that structure is real but fragile in the face of scale. It shows that the night sky you are used to is not a universal feature but a local privilege of being inside a galaxy rich in neighbors. And the most useful outcome of this perspective is not sadness, but clarity. The universe is not obligated to be intuitive, but it is consistent. That consistency is what makes science possible. It is what allows missions like Gaia to map stellar motions, what allows parallax to become distance, what allows spectral shifts to become velocity, what allows a faint smudge of intra-cluster light to become evidence of countless exiled stars. A lonely star is hard to find because it is far away, and because the universe is vast. But once it is found, it does not ask for interpretation. It offers a simple, steady lesson. Physical law holds even in the emptiest places, and the cosmos does not need to notice in order to be understood. A star begins life in company, even when space is mostly empty. It forms inside a galaxy where gravity has already done its long work of gathering matter into structure. Gas and dust drift through cold molecular clouds. A denser pocket collapses under its own weight. Heat rises, pressure rises. And then, when conditions become intense enough, nuclear fusion ignites in the core. Hydrogen begins turning into helium, and a new light is added to the galaxy's ongoing glow. From that moment, the star is not simply shining. It is participating in a vast gravitational choreography. Inside a galaxy like the Milky Way, stars orbit the galactic center in long paths measured in hundreds of millions of years. They move quickly, yet remain bound because the galaxy's mass is enormous. Much of that mass is not visible. Dark matter forms a halo around the galaxy, deepening the gravitational well and extending the region of influence far beyond the bright spiral arms. Vera Rubin's work on galaxy rotation curves helped reveal this hidden architecture, showing that galaxies are not held together by starlight alone. So most stars are members. They belong in the only sense the universe recognizes. Their motion is bound to the system's gravity. But near the center of a galaxy, the rules can become sharper. Supermassive black holes sit in those regions, shaping the orbits of nearby stars, and occasionally creating conditions where gravity does more than hold things together. In rare cases, gravity rearranges energy so violently that it breaks membership. That is where the Hill's mechanism enters the story. A binary star system wanders close to the supermassive black hole. The gravitational field is not uniform across the pair. Tidal forces stretch the system. The bond between the two stars is disrupted. One star can be captured into a tight orbit around the black hole, becoming part of the crowded central environment. The other receives an enormous transfer of energy and is flung outward at extreme speed. Nothing is pushed. Nothing is fired. No explosion is needed. It is simply gravitational dynamics guided by conservation of energy and conservation of momentum. A three-body interaction redistributes the system's energy budget, and one star leaves with enough speed to exceed galactic escape velocity. That is the moment the loneliest story begins. Not with sadness, but with a threshold. When a star becomes a hypervelocity star, its path changes from a bound orbit to an unbound trajectory. It may still pass through the galaxy's disk, but it does not loop back. It moves outward through thinning starlight and into the galactic halo, where stars are fewer and the scenery grows quieter. Eventually, it reaches the far outskirts where the visible galaxy has already faded into a distant shape, and where the dark matter halo, though still exerting gravity, can no longer keep the star tethered. Then the star crosses into intergalactic space. Intergalactic space is not a mystical void. It is a physical environment with measurable properties. The intergalactic medium contains extremely thin gas, mostly hydrogen and helium, spread so sparsely that a region can contain roughly one atom in a volume the size of a room. Dark matter also remains present on large scales, shaping the cosmic web into filaments and nodes where galaxies and clusters assemble, leaving vast cosmic voids between them. In those voids, the density drops even further and structure becomes a distant rumor. If a star drifts through such a region, there may be no nearby suns for millions of light years. There may be no rich background field of stars. There may be no constellations, because constellations are not a property of the universe. They are a local accident of being inside a galaxy dense enough to draw patterns. From close by, the star is bright. From far away, it is one more small light among distances too large to be friendly. And yet, for the star itself, almost nothing changes inside. Nuclear fusion continues. Hydrostatic equilibrium remains. Gravity presses inward. Pressure pushes outward. The core keeps turning hydrogen into helium, governed by the same physics that applies to stars in spiral arms and star clusters. Isolation does not dim fusion. The star does not require an audience. What isolation changes is the star's relationships. Inside a galaxy, a star may pass near molecular clouds, be nudged by other stars, exchange mass with a companion, or wander through environments that reshape its long-term evolution. Between galaxies, almost none of that happens. The star's story becomes simpler, almost pure. A self-contained fusion engine drifting through a space that offers very few interruptions. That drifting, however, takes place within a universe that is also changing. On the larger scales, cosmic expansion increases the distance between unbound objects over time. The star is not stretched, and any planets that remain close to it are not stretched either. Bound systems resist expansion because local gravity and other forces dominate. But beyond those local islands, the background trend remains. Unbound regions separate. So the star's exile becomes more permanent in a very literal way. It is not only far from home. The universe's expansion makes the concept of return less meaningful over long spans of time. Bound structures become islands. the space between them grows. Light from distant galaxies becomes more redshifted. Some regions become so far away in practice that their light may never arrive again. This is where the phrase, "the brightest thing in the emptiest place," earns its weight. Brightness is local. Emptiness is global. Near the star, light is everything. It defines day and night for any worlds that might still circle it. It shapes temperature, weather, chemistry, and any hope of biology. Even if a planetary system is partly stripped during the ejection, it is not impossible that some close-in planets remain, the ones most tightly bound to the star's gravity. If they exist, they would orbit as faithfully as planets anywhere, while their sky remains almost blank except for the star that keeps them alive. Far beyond that small sphere, emptiness dominates. Galaxies become faint smudges. The cosmic web becomes an abstract structure rather than a visible one. There is no thick band of starlight like the Milky Way because there is no local crowd of stars to create it. Yet the universe is never perfectly dark. The cosmic microwave background radiation fills all of space as a faint afterglow of the early universe, mapped in detail by missions such as the Planck satellite. It is not a glow that human eyes would notice, but it is a reminder that even the deepest void is still part of the same cosmos, carrying the imprint of its earliest moments. And while the star drifts, time continues to do what it always does. Depending on its mass, the star may remain stable for billions of years, or far longer. Eventually, it will change. It will exhaust core hydrogen. It will evolve. It may end as a white dwarf cooling slowly in the dark. It may end as a neutron star, a dense remnant with physics pushed to extremes. It may end as a black hole, a region of space-time where gravity dominates in its most complete form. Those outcomes depend on mass, not on scenery. In the far future, if the universe continues its long march toward higher entropy, starlight becomes rarer. Star formation slows as usable gas is consumed or dispersed. Existing stars burn out, remnants cool. The cosmos trends toward heat death, a state where energy gradients become small and structure becomes harder to sustain. Even black holes in the deepest times may evaporate through Hawking radiation, leaving behind a quieter universe still. In that context, the lonely star is not an exception to cosmic history. It is an honest participant in it. It simply occupies a place where the universe's emptiness is harder to ignore. And that may be the most important point to carry gently back home. Loneliness in this story is not a moral condition. It is not tragedy. It is geometry. It is gravity. It is the difference between being bound to a massive system and being launched beyond its reach. It is the consequence of a rare encounter near a supermassive black hole, the logic of the Hill's mechanism, and the fact that conservation laws can produce outliers as naturally as they produce stability. The universe does not notice. It does not need to. But humans do notice because minds are built to recognize patterns and to feel the weight of scale. A star drifting between galaxies confronts intuition with something simple and difficult. There are places where the sky would hold almost nothing at all. There are distances that can be described, calculated, and still not truly imagined. There are processes that take billions of years and still count as ordinary in cosmic terms. And yet, against all that distance and time, the light remains simple. A star shines because gravity compresses matter until fusion begins. It shines because equilibrium is maintained. It shines until fuel runs out or conditions change. Whether it shines in a spiral arm surrounded by neighbors or in a void where galaxies are faint scars in the distance, the mechanism is the same. The laws are stable. The outcome is predictable in its broad outline, even when the details are vast. So the loneliest star in the universe becomes a quiet demonstration of what physics does best. It turns a dramatic idea into a measurable one. It replaces metaphor with mechanism. It shows that exile can be defined in terms of velocity and binding energy, and that emptiness can be described in density and distance. And then, without forcing the point, it offers a gentle return to the local truth that is easy to forget. Here, inside a galaxy, the night sky is not empty. It is crowded with light, even when city glare hides most of it. There are stars bound together by a shared gravitational home, orbiting a center they will never reach, held by a halo of dark matter they will never see. There are neighboring suns only a few light years away. There are galaxies beyond and clusters beyond those, and a cosmic web that links structure across unimaginable distances. Somewhere out there, a star has been thrown away into the dark. Between all that structure, it keeps shining anyway. And in that steady light, traveling through the emptiest place, the universe quietly proves a final point. Belonging is local, law is universal. And even in the deepest darkness, physics remains perfectly, calmly consistent.